A small block of mass m equal to 0.021 kg can slide along the frictionless loop with loop radius r equal to 16 centimeters. The block is released from rest at point P at height h equal to 5r above the bottom of the loop. What are the magnitudes of A, the horizontal component, and B, the vertical component of the net force acting on the block at point Q? C, at what height h should the block be released from rest so that it is on the verge of losing contact with the track at the top of the loop? So considering the free body diagram of the block at point Q, so say this is the block, we have two forces acting on the block. One is the vertical weight of the block, well, the weight of the block, which is vertical, so I'm gonna call that Fy, which is mg. And then the second one is the reaction of the loop on the block, and that's equivalent to the centripetal force of the block, and that would be acting this way, which is m times centripetal acceleration, which is v squared over r. So centripetal acceleration is v squared over r, so times the mass will give you that force, and I'm gonna call this Fx. So question A requires us to find Fx, which is equal to mb squared over r, and question B, well, question B is just the mass times gravity, which is easy to find. We have the mass and we know what gravity is. So one thing we need to find for sure to be able to find the horizontal component is the velocity at Q. So to do this, we have to consider two relationships, and we have to use the conservation of energy. So what I'm saying is the energy, the total mechanical energy of the block at point P is conserved. So it is equal to the total mechanical energy at point Q. But remember, it was released from rest. So the velocity at point P is 0. And then the height at point P is, I'll leave it as h. H was given as 5r, but I'm gonna solve it generically with h as the height. So the energy at point P is the potential, the kinetic energy at point P. Zero velocity means no kinetic energy, plus the potential energy mgh. So I'm just gonna say mg HP. I know HP is 5r. So E energy, total energy at point P is simply mgHp, right? I'll call this 1. Now, what is the total energy at point Q? So EQ. We need to find that. First thing first is that we know it has a velocity VQ, which is what we are calling V up here, and then we have a height, which I'm gonna just call HQ. HQ here is equal to R, as we can see in the figure, is equal to R, but I'm gonna solve it generically again. So EQ will be equal to the kinetic energy at point Q, which is 1/2 mv squared, plus the potential energy there, which is mg. I will leave this as HQ for now. Call this equation 2, right? Now we can equate both equation 1 and 2 to each other, and then solve for v squared. Now we would have mg hp is equal to 1/2 mv squared. What we are trying to solve for is v HQ. So I can take this portion to the other side. So we have mg hp minus HQ is equal to 1/2 mv squared, right? So now I can multiply both sides by 2 and divide both sides by m. By so doing, I would have 2g bracket hp, height at point P, minus height at point Q, is equal to v squared. And this is actually what we need. We don't really need v, we need v squared, because fx is mv squared. So from above we have that fx is mv squared divided by r, but we have that v squared is given by this expression on the left hand side of v squared. Therefore we have fx is equal to 2mg. I'm substituting this expression in place of v squared. So we have 2mg bracket height at P minus height at Q, and then divided by R. This will be the expression for the horizontal component of the net force. Now we can plug in values. I solved it this way, so we have a generic expression where we can just plug in values. So going back, we have that R is 16 centimeters. Well, before doing that, HP was given as 5R. If you look at the diagram, well, not the figure, I mean, HP is 5R and we have HQ as R. So we can plug in those values. So HQ is R, so we can have a more simplified expression for Fx. Therefore Fx will reduce to 2mg. This is 5R minus R, which will give me 4R, right? 4R. So we have this will reduce to Fx equal to 2mg times 4. Why? Because this will be 4R and r will cancel r and we'll be left with 4. So Fx is simply 8 mg. That's the expression for the horizontal component of the force. And when you go back, m is 0.021 and r is, well, we don't need r in this because they all cancel out. Therefore, for this specific question, Fx will be 8 times 0.021 times 9.81. And I'm just gonna press this out using, punch it out in my calculator, times 9.81, and this gives me a value of 1.648 Newton. Now remember, from our free body diagram, the vertical is just the weight of the block. So for question B, we have Fy is just mg. So by plugging in the mass, which is 0.021, we multiply it by 9.81, and that will give me 0.021 times 9.81, and that will give me 0.206 Newton. 3 decimal places. Question C, I will go back to it so we can remember exactly what the question says we should find. It says, what height must we release the block such that the block is at the verge of losing contact with the loop at the top. So one thing we need to understand is what that means. So I'm just gonna sketch something that looks like the loop. It's not accurate, but it's good enough for the explanation. So at this top, if the block is at the verge of losing contact with the loop, it means the whole force, net force, it implies that the net force here is equal to 0. F net equal to 0. So what are the forces acting here? The two forces acting here is the the weight, which is mg, and the centripetal, which is mv squared over r. So these two forces have to cancel out, and from this we can find the velocity at this point. So that's one thing. And we know that the height of the block at this position, the height of the block from the base of the loop is 2r. So we have the from this net force, we can find the velocity, that is mv squared over r has to be mg. M cancels m, so we have v squared equal to rg, right? Also, so with having gotten the velocity and knowing the height, you can find the total energy here. So I'm gonna call this E top. That's total energy at the top is gonna be equal to the kinetic energy, which is 1 over 2 v squared, mv squared, which is rg, plus mgh, h is 2r. So yeah, mg times h, and the height there is 2r. So we just need to equate this expression to the height at the top where it should be released from. So I'm going to call the point of release, the energy at the point of release, E, should I call it EP? Let me look at this. At what height? I'll just call it EP. And the energy there is just potential because it was released from rest. It's expected to be released from rest, so it will be mgh or mhg. So we have energy at that point of release must be equal to energy, total energy at the top of the loop. So we have mgh, which is EP, is equal to 1 over 2 mrg plus 2 mrg. Okay, let me write this well. Now we can factor out m from these two, and it's gonna cancel this. Likewise, g can be factored out from everything, so we simply have h. Well, I'm gonna write it out instead of just saying it. So we have mgh is mg bracket r over 2 plus 2r, right? So now mg cancels out, and we have the height from which it should be thrown must be equal to r over 2 plus 2r. And when you simplify this, this should give you, this is the same thing as 4 over 2, so this will give you 5r over 2. This is the expression for the height at which the block should be released, such that it is at the verge of losing contact with the loop at the top of the loop. Now for this specific question, r is 16 centimeter, which is equal to 0.16. Therefore, h is 5 times 0.16 over 2. I'm going to punch this out in my calculator, divided by 2, and this gives me a value of 0.4 meters or 40 centimeters. Thanks for watching.